All right, so this is an introduction to chapter 6. We're going to focus on using normal distributions. And that means we are going to be working with continuous random variables. So this means that we're going to change things up a little bit. It also means that it's time for me to introduce a very important concept. And before I introduce the very basic concept, I want to talk about a really simple, a really simple type of probability distribution. This is what we call a uniform probability distribution. And in this uniform probability distribution, all outcomes have the same chance of occurring. And let me give you a couple of examples of a basic uniform probability distribution. You really have a lot of experience with them. I'm going to give you 3 of them right off the bat. A fair coin toss. Notice I said fair. A fair coin toss. There are 2 outcomes, heads and tails. The probability of a head, 1 out of 2. The probability of a tail, 1 out of 2. Same probability for each outcome. Fair dice tosses. When you toss dice, you have a 1, a 2, 3, a 4, a 5, or a 6 in our sample space. I like to put my little set brackets around those guys. It's not entirely necessary, but that's the way I like it. I won't list them all, but I'll note the probability of a 1 is 1 out of 6. The probability of a 2 is 1 out of 6. And the probability of a 6 is 1 out of 6 too, as well as everything in between. So they all have a probability of 1 out of 6, the same probability of occurring. That is a uniform probability distribution. A fair deck of cards. I'm not going to list them all, but there are 52 distinctly different cards. Each with a probability of whatever that card is of 1 out of 52 of being drawn. If you've got a fair deck of cards, and they're not all aces, say. So they all have the same probability, 1 out of 52 of being selected. These are examples of uniform probability distributions. And I'm going to take a look at the dice example. I want to draw a particular sort of picture. I'm going to draw a graph of the probability distribution for fair dice. So the vertical axis is probability. The x-axis is the outcome. of rolling or throwing the dice. You can have a 1, a 2, a 3, a 4, a 5, or 6. I am going to associate this with a histogram for rolling a 1 if you land between, say, a 0 and a 1. 2, and so on and so forth. The reason I'm setting it up like this, it's a little bit different than you might see set up in perhaps some other parts of the book, but right now it's the one we want. So I have my outcomes visualized in this fashion for a particular reason. If I take a look at the area covered by this histogram, I note that the area is length times width. The length, 0 to 6, is 6. The width of that rectangle is 1/6. So it's 6 times 1/6, or 1. And I'll remind you, every probability distribution has to sum to 1. So what we're trying to make clear here is that the area in this particular picture is equal to probability. So area and probability are going to become the same for us in this course. Here's the reason for that. See, area is something that we can measure, like in real life. Probability is a human notion. It doesn't exist in the real world. You can't go pick something from the tree of probability and cook it up for dinner. It doesn't work that way. So what do? What we do is we come up with a quote unquote proxy argument. Area is a stand-in or a proxy for probability, and it works quite well. Notice, if I want to find the probability of rolling a 2 or a 3, I can literally sum the area of these two outcomes to find the probability. You'll notice that the word or means we've got the addition rule, but unlike chapter 4, we have these events are mutually exclusive. So I can calculate area here and make that probability. You'll notice that we've got a width of 1 times a height of 1/6 plus a width of 1 times 1/6, or 1/6 plus 1/6, better known as 2/6 or 1/3. So the probability of a 2 or a 3 is a 1/3. So it's important to realize that at this juncture, area and probability will now be regarded pretty much as the same. I could have made this argument earlier with histograms and the like, but there's too much else going on. Now it's really time for it. In fact, we cannot proceed without this particular notion or idea. So there we go. This is the notion of a uniform probability distribution. It's important because it's a way to get into this notion of area as probability, which is really vital for the balance of our course. Now, let me go ahead and talk about a particular type of distribution. We talked about it somewhat. I'm going to make it a little bit more precise. I'm going to talk now about normal distributions. For example, we know these are already, well, we already know that they are bell-shaped distributions, and there's a couple of other requirements that you'll remember from chapter 2. values are pretty much the same on the way up as the way down. There's a bit of symmetry there too. We call it bell shape because when we draw it, it draws like a bell. Now, what is going to be on the vertical axis is a probability, very much like the picture I just drew with the dice. The x-axis is going to be outcomes or values again, but it's important to realize that we use this with a continuous random variable. So that adds a certain amount of complexity to this. So, for example, if I talk about IQ, we know that the mean is 100, the standard deviation is 15, and it is approximately normal, or more accurately, it is approximated very well by a normal distribution. So, here's my normal distribution, the bell-shaped curve. They're easy to draw. The mean is now 100. The vertical, this is again x, there is a 0 over here somewhere. The vertical axis again is probability. But because this is a probability distribution, there are certain requirements. The biggest requirement is that the area under this graph and above the x-axis equals 1. So the total area is equal to 1 because this is, at the end of the day, a probability distribution. Now, I'm going to take a look at a very specific probability distribution that we'll encounter in section 6.1. And this is what we call the standard normal distribution. My only goal here is to introduce it and say, hey, hello, pleased to meet you. We'll actually use this a lot in 6.1 and at other places throughout the balance of the semester. But all I really want to do here is to really get across the basics of this standard normal distribution. I'm not even really going to use any of my TI-84 tools tonight. I'll start that tomorrow night. But I do want to introduce this notion of a standard normal distribution. What do we mean by a standard normal distribution? Well, I note, I'm sorry, I love my colors here. I note we're talking about a normal distribution, which means bell-shaped. The standard normal distribution has a mean of 0 and a standard deviation of 1. That's what makes it a standard. So keep that in mind. If I ask you about the standard normal distribution, it always has a mean of 0 and a standard deviation of 1. This is also called the Z distribution. Yes. That Z from Z-scores. Same Z. The standard normal distribution is also called the Z distribution. I use the terms interchangeably, although on quizzes and exams, I usually use the word standard. Well, it's standard. And it is a probability distribution. You have the horizontal axis. This time I call it Z, but it's just like X. There's my normal distribution. Probability is recorded on the vertical axis. We have a mean of 0. So the mean is right there, right on the quote unquote sort of so-called y-axis. And very, very much like I just said in the previous slide, the area is equal to 1. So if I take a look at the area between the curve and the x-axis, it's equal to 1. Now, there's a couple of interesting things about this distribution. First off, there is no quote unquote x, or I guess it would be z intercepts. This graph continues all the way out here, just like that, to positive infinity, never really getting down to the z or horizontal axis. It happens at the other end of the spectrum too, at negative infinity. And it's actually going to be important to realize and utilize that when we get to employing the tools that we're given to make calculations regarding this type of distribution. So what we'll do is we'll find probabilities or scores, and I'll leave that for tomorrow's lecture, but I will note that with a mean of 0 and a standard deviation of 1 for the standard normal distribution, if I take walks away from that mean of 0, taking steps of 1, I encounter something that we talked about way back in chapter 3.2. So plus or minus 1 standard deviation, we get about 68% of all outcomes. Plus or minus 2 standard deviations, we get about 95% of all outcomes. Plus or minus 3 standard deviations, we get about 99.7% of all outcomes. So the empirical rule is still in effect. It's still there, and we actually make a fair amount of use of that as we make our way through the balance of the semester. Furthermore, there is a direct connection between probability and area, because the total area of that graph is equal to 1. What that means is, for example, this little bit of area between plus or minus 1 that area in here, 68% of everything, or 0.68. So if I were to pick a z-score at random, the probability it falls somewhere between -1 and +1 is 0.68. So, as I say, there is a real strong connection between probability and area. And we like to calculate probabilities by actually calculating area. And that's really the secret to a lot of statistics, at least the calculation of a lot of different probability circumstances. We find the appropriate probability function. The area will be equal to 1. We figure out where we need to measure, and we measure some area to find a probability. Because as I say, area is a proxy for probability. So that truly is about all I want to say for my introduction to chapter 6. Now I'm going to go ahead and jump back to my other camera. Stop my recording.